Welcome to the Deep Dive. We take the sources you send us, unpack them, and pull out the insights. And today, wow, we are really taking a leap. We're looking beyond the reality we see every day. Our mission, really, is to try and understand the universe's best magic trick, the possibility of extra dimensions.
Yeah, it's quite a trip we're taking. We're investigating one of the strangest, but maybe one of the most, well, beautiful ideas in physics. One of our sources actually used that great quote, it must be beautiful because it is so hard to see, which feels very fitting here.
Definitely. And we're diving into these hidden passages, these extra dimensions, to try and crack what's maybe the biggest puzzle in physics today.
Right.
Which is the hierarchy problem.
Right.
Basically, why gravity is just so incredibly, ridiculously weak compared to everything else.
Exactly. But before we even get to gravity, we need to get a handle on dimensions themselves. We know our three spatial ones, right? Up, down, left, right, forward, back. You need three coordinates, three numbers to pinpoint anything in our space.
Like the character Ike. In one source, his life needed three variables. Age, how much he lost gambling, how often he drove his car. A three-variable world.
Yeah, exactly. He needs those three things. But mathematically, there's nothing stopping us from defining a space with 5 dimensions or 10 or 100. You just need more numbers, more variables.
The tricky part is, why can't we, as three-dimensional beings, actually see or sense another spatial direction? That's the real mind-bender.
And that's where the classic analogy comes in. You almost have to talk about Edwin Abbott's Flatland from, 1884?
Like the 2D world, beings living on a flat sheet of paper.
Exactly. So imagine a 3D object, like a sphere, passing through their 2D world. What do they see?
They don't see a sphere. They just see the slice, the cross-section, little disc that appears, gets bigger, then shrinks, then disappears.
Precisely. They just can't grasp the third dimension. Not really, unless something physically lifts them off their 2D plane. And the point is, we might be the Flatlanders here. Just because we can't perceive a fourth spatial dimension doesn't automatically mean it isn't there.
It just means we might be confined, stuck in our 3 dimensions.
Stuck on our brain is the term we'll get into. Unable to move sort of up into that extra direction.
Okay, so if these extra dimensions exist, where are they hiding? If they're not obvious, like length and width?
Yeah.
How could they be missed?
Well, the earliest idea really comes from Kaluza and Klein back in the 1920s. Their theory suggested that maybe these extra dimensions are compactified. Meaning curled up, rolled up incredibly tightly, so small that they're basically invisible at the scales we normally interact with.
Okay, this is the garden hose analogy, right?
That's the one. From far away, a hose looks like just a 1D line.
We'll get up close.
Get up close, and you see it has a surface, a circle, a second dimension, but it's curled up and tiny compared to the length.
So these extra dimensions could be like that circle on the hose, just incredibly tiny, like plank length tiny.
Potentially, yes.
Okay.
Like 33 centimeters small. If a dimension is curled up that tight, any effects or changes happening within that tiny curled space are almost impossible for us to detect directly.
And these changes, these sort of ripples in the tiny dimension, those are the Kaluza-Klein modes.
Yes, exactly. KK modes. And this is crucial for you listening. These modes, these vibrations in the extra dimension, from our 3D perspective, they look like new particles.
Heavy particles.
Typically very heavy particles to the ones we already know. They're like the fingerprint that the extra dimension leaves behind in our world.
Okay, so tiny curled up dimensions, maybe leaving fingerprints as heavy particles. Got it. But why are physicists so keen on this idea? It seems pretty exotic.
It comes back to that giant puzzle,
Yeah.
the hierarchy problem. Why is gravity the odd one out? Why is it so fantastically weak?
It really is a huge gap, isn't it? Can you give us the numbers again?
Okay, so the energy scale where we think gravity should become strong, like the other forces, is the Planck scale. That's around 10 GeV, billion electron volts.
Okay, huge energy.
Huge. But the scale where we see particle masses actually set, like the Higgs boson mass, that's the weak scale. And that's only about 250 GeV.
So 1019 versus 250, that's 16 orders of magnitude.
16 orders of magnitude, 10 quadrillion. Gravity appears 10 quadrillion times weaker than the weak nuclear force at its own scale. It's just bizarre.
And physics doesn't like that kind of disparity.
No.
Right? It suggests something's missing, or we need this fine-tuning.
Exactly. Fine-tuning is the nightmare scenario. It means that in our theories, to keep the Higgs boson light and stable, you have to assume some underlying parameters cancel each other out with, perfect precision.
Like winning an impossible lottery, as one source put it, guessing a 16-digit number first try.
Pretty much. It requires this incredibly delicate balance, canceling huge numbers to get the small number we observe. It feels unnatural, rigged. We'd much rather have a reason for the weakness.
A natural explanation, not a lucky coincidence.
Yes. And that's where the brain world idea really took off. It offers a geometric explanation.
Okay, let's talk brains. The sources describe them as membranes, slices, living inside a bigger space.
Yeah, think of them like that. Membranes, or brains for short. They're sort of boundaries or surfaces existing within a higher dimensional space, which we call the bulk.
And the key idea is, we live on one of these brains, our entire observable universe.
That's the hypothesis. Our 3 spatial dimensions plus time make up one brain, a brain world.
But why are we stuck here? Why don't we or our particles just float off into the bulk?
Well, the idea is that most forces and particles, electromagnetism, the strong and weak nuclear forces, all the quarks, electrons, photons, they are intrinsically linked to the brain. They can't leave it.
Like things stuck to the surface.
Sort of. Think of it like chalk dust on a blackboard. The dust can move all over the 2D blackboard, but it can't just leap off into the 3D classroom.
Okay, but there's one exception.
Gravity. That's the crucial difference. The particle thought to carry gravity, the graviton, isn't stuck. It's unique because it can travel freely through all the dimensions.
Through our brain and into the bulk, the extra dimensions.
Exactly, and that could be the answer to the hierarchy problem.
How so?
Well, if gravity, unlike the other forces, spreads its influence out into these extra dimensions, its strength gets diluted.
So when we measure it here on our brain, we only feel a fraction of its total strength because most of it has leaked away.
That's the core idea. Gravity isn't fundamentally weak. Its strength is just spread out over more dimensions than the other forces experience. The full strength is there in the bulk, but we only feel the part that intersects with our 3D world.
That is a really elegant way to think about it. It's not weak, it's just diluted.
It provides a potential mechanism, yeah. And this brain world concept led to basically 2 main types of models, 2 different ways this could actually work.
Both trying to solve that massive hierarchy problem using extra dimensions.
Well,
what's the first one?
The first is maybe the more startling one initially. It's called the Large Extra Dimensions model, or the ADD model, after the physicists Arkani Hamed, Dimopoulos, and Diwali.
Large? Wait, I thought we were talking about tiny, curled-up dimensions.
That was the old Kaluza-Klein idea. ADD turned it on its head. They realized if the standard model particles are truly stuck on the brain...
The particles we're made of.
Right. If we can't leave the brain, and only gravity can, then maybe the extra dimensions don't have to be Planck scale tiny. Maybe they could be. Well, large.
How large are we talking?
Potentially up to maybe 1/10 of a millimeter across.
1/10 of a millimeter? That's huge. I mean, in particle physics terms, that's absolutely enormous, right? You could almost see that.
It sounds enormous, yes. Devastator, as one source puts it, gigantic. But think about why they could still be hidden.
Because only gravity feels them.
Exactly. And how well have we actually tested gravity, Newton's inverse square law, at really short distances?
Not that well, I guess.
Until fairly recently, reliable tests only went down to about the millimeter scale. So if these extra dimensions were, say, 1/2 millimeter across or 1/10 of a millimeter.
They'd be just under the radar of our previous gravity experiments.
Wow. Okay. That's one way. What's the alternative?
The alternative is the model developed by Lisa Randall and Raman Sundrum, the RS model. This one doesn't rely on the dimensions being physically large. Instead, it uses geometry. Warped geometry.
Warped. Like curved space-time.
Precisely. The RS model typically uses just one extra dimension, but it's not flat like a sheet of paper. It's highly curved, maybe like the inside of a funnel or a saddle shape. And it's bounded by 2 brains.
Okay, 2 brains now.
Yeah. Let's call them a gravity brain, where gravity is fundamentally strong, Planck scale, and the weak brain, which is where we live.
So we live on the weak brain in this warped dimension. How does the warping help with the hierarchy problem?
The curvature itself does the work. Because of the specific way space-time is warped, energy scales and masses get dramatically rescaled as you move across the extra dimension.
Rescaled how? Exponentially. So things that have enormous mass or energy near the gravity brain appear to have exponentially smaller mass and energy when viewed from our position on the weak brain.
Whoa. So the Planck scale masses on one brain just naturally look like weak scale masses around 1,000 JV or so on our brain, just because of the curved geometry between them.
That's the beauty of it. The huge hierarchy in scales emerges naturally from the space-time geometry itself. No fine-tuning needed. The weakness of gravity for us is just a consequence of our location in this warped space.
That feels almost more elegant in a way,
Right.
using the shape of space itself.
It's a very compelling idea mathematically. Physics is doing the work, not arbitrary numbers.
Okay, so we had these two main ideas, large extra dimensions, ADD, where gravity dilutes into big spaces, and warped extra dimensions, RS, where geometry rescales everything. Mind-blowing stuff. But how on earth do we test these? How do we find evidence for dimensions we can't see?
Right, that's the critical question. Theories are great, but physics needs experiments. The key signature, the smoking gun for any extra dimension model, would be detecting those Kaluza-Klein modes we talked about earlier.
The heavy partner particles?
Heavy partner particles, they are the unavoidable consequence of having extra dimensions, and they would leave detectable effects in our 3D world.
So how are we looking for them?
There are basically two main frontiers: low energy, high precision tests, and high energy collider experiments.
Okay, low energy first. Yeah, like testing gravity very carefully at short distances.
Exactly. Experiments like Eat or Wash use incredibly sensitive devices, torsion balances, to check if Newton's inverse square law holds up at scales below a millimeter.
And if the ADD model, the large dimensions model, was right.
Then gravity should deviate from the inverse square law at those short distances because it would start leaking into those extra dimensions noticeably.
What have those tests found so far?
They've pushed the limits quite hard. The current results tell us that if there are large extra dimensions, like in the ADD model, they have to be smaller than about 0.1 millimeters, maybe even smaller. So it constrains that model, but doesn't rule it out completely yet.
Okay, constrained but not dead. What about the high energy frontier? The Large Hadron Collider, the LHC.
The LHC is where things get really interesting because it could potentially produce these KK particles directly, and the signatures depend dramatically on which model is right.
How so? What would the ADD model predict for the LHC?
In the ADD model with large dimensions, collisions could create KK partners of the graviton, but because these gravitons can travel freely into the large bulk,
They just disappear.
exactly, they'd escape from our brain, taking energy and momentum with them, vanishing from our detectors. We wouldn't see the particle itself.
Would see missing energy, like something flew off stage without telling us.
Precisely. A characteristic signal of energy imbalance in the detector. It's a classic signature. It's how the neutrino was first inferred, remember. Energy seemed to vanish in beta decays. Finding large amounts of missing energy in specific patterns at the LHC could point strongly towards the ADD model.
Okay, missing energy for ADD. What about the warped model, the RS model? What would that look like at the LHC?
Totally different. In the RS model, the KK gravitons are typically much heavier, but crucially, they are expected to decay visibly within our detector.
So they don't just disappear.
No, they stick around long enough to decay back into standard model particles we can detect, like pairs of electrons or photons or quarks.
And they'd have a specific characteristic.
Yes, a very specific one. These KK gravitons would have what physicists call spin 2. It's like their identity card, proving their connection to gravity. Finding a new, heavy spin 2 particle decaying into familiar stuff would be a bombshell discovery.
A clear spike in the data at a specific high mass.
A very clear, resonant spike. It would be a much more direct and unambiguous signal than just missing energy. It would scream, warped extra dimension.
Wow. So the LHC is hunting for two very different signs, either particles vanishing into large dimensions or new heavy particles appearing from a warped one. Either result would be, well, revolutionary doesn't even cover it.
Absolutely. It would fundamentally change our picture of reality. We've gone from extra dimensions being purely mathematical speculation to having concrete testable theories like ADD and RS brains, warped geometry. These aren't just sci-fi anymore. They're real physics concepts being actively searched for.
And they offer a potential solution to that deep, nagging problem of why gravity is so weak.
A geometric solution which feels much more satisfying than just accepting fine-tuning.
It really makes you think differently about space, our entire universe, maybe just a 3D slice floating in something much bigger and more complex.
It does, and maybe the most profound implication, the real provocative thought that comes out of all this, it's something hinted at by physicists like Edward Witten. Based on these kinds of ideas where the dimensionality we perceive might depend on where we are or what energy we're probing, Witten suggested that maybe space and time may be doomed.
Doomed, as in not fundamental.
Exactly. Is space-time itself the basic fabric of reality? Or is it just an emergent property, something that arises from a deeper, stranger structure underneath? If the number of dimensions isn't fixed, maybe space and time as we know them aren't the final story.
That's a lot to chew on. Is our familiar reality just a shadow of something else entirely?
It's perhaps the deepest question these ideas force us to confront. Something to definitely mull over next time you feel confined to just 3 dimensions.